Hello and welcome back to the lecture 1 of this series QM101. Today we will be discussing how do we define states in classical and quantum physics. It's going to be a really short lecture, but this is also going to be the most important lecture, I guess, because this defining state is the fundamental difference between classical and quantum physics, and you shall see soon how. So first of all, what do we mean by state? State basically tells you the configuration. Basically, you can say state and configuration are sort of synonymous here in the sense, but a state of a system is basically the configuration of the system in which the system is in. Okay, I hope that, although these two are synonymous, I hope you get the idea. So suppose, for example, if you want to study the motion of the particle in classical physics, then the state of the system is its position, the position vector r, and its velocity maybe, or the momentum, and there can be other quantities like energy, and there can be that. If you're studying a gaseous system in a container, then there can be quantities like pressure, volume, number of particles, temperature, etc. So all these variables or quantities which describes the configuration of a system, these are what we call state variables. Now, the most important thing is to notice here is that all these state variables which we use to define state in classical physics, like the position or momentum or the pressure or the volume, all these things are measurable quantities. Measurable quantities as in you can measure what is the position with respect to some coordinate, or you can measure the pressure of the gas in a container or the volume of the container of gas. You can also measure energy of a system. So, and these measurable quantities, they have a very technical name which is often used in physics. They are called observables. Observables means the quantities which can be observed or measured. You can observe by measuring them, so it's again synonymous, observable, measurable in some sense. So in classical, the most important point to notice is that in classical physics, the state of a system is defined by a set of observable quantities. Whereas in a quantum system, the state of the system is not defined by an observable quantity. The state of a system is something more mathematical or more fundamental or more abstract in some sense. So in quantum mechanics, I'll use abbreviation QM for quantum mechanics. The state of a system is defined by a more abstract quantity, which we can call state vector. Now what is this state vector? It's a vector in Hilbert space. So again, now what is a Hilbert space? So Hilbert, okay, so I might not be making much sense here. Let me try to give you an idea. So Hilbert space is a vector space which has a inner product defined on it. Now I hope you are aware of this term vector space and inner product and all, but if you are not, I would recommend you to go through these topics. Vector space, inner product, these are topics of linear algebra, and there's a YouTube lecture series of a different channel which I can recommend you. It's like the lecture in that series are very short, so I hope it, like, you can just watch 3-4 videos and you don't need to watch all of them to understand what is a vector space and what is an inner product and what is a Hilbert space and all. I'll put all those video in the description. So now, for now, you can just think of Hilbert space as some set, and vector space and inner product space, these are basically some structure defined on that set. So in fact, that's how we define space in mathematics. Space in mathematics is some set plus some structure on that set. And different structure leads to different kinds of spaces: vector space, metric space, topological space. In fact, a group is also a sort of space in that sense. So, and this Hilbert space which we are talking about, it has like several properties. It is a vector space, it is also an inner product space, and it also has more structure which leads to the name of Hilbert space. This Hilbert space is some abstract vector space. Okay, it is not some real vector space as we see in classical physics. Like in classical physics, what we do when we define the position vector, we have the real space, the space which is around us, and we define the position as a vector in this space around us. But when you, so this is the case with position, but as soon as you go to say measuring the velocity, so the velocity is not really a vector in the space around us. It is in some different space which is mathematically same as the space around us, but it is different from the space in which we live. So the vector space of velocities or momentums, it's different from the space around us. Like basically they are two separate things, the vector space of position and the vector space of velocities or vector space of momentum, but they are isomorphic to each other. That is, they are mathematically the same. Basically what you can do in one, you can do that in other as well, and that is the reason you cannot add position and velocity, because they are vectors in entirely different space, and there is no natural addition defined on these two vectors, like on these two separate vector spaces. But you can add two positions and you can add two velocity vectors because they live in the same vector space. Now, just like this position space, just like this velocity vector space, Hilbert space is also some abstract mathematical space. But the difference is that velocity, although it's lives in a vector space which is different from our space, but it is isomorphic to it, and we have some way of measuring the velocity. Whereas these vectors in Hilbert space, these are not some measurable vectors, these are some abstract vector. Abstract as in they are only mathematical in nature. So we define a quantum state using these vectors in Hilbert space, and these vectors are denoted by generally ket. So some terminology, a vector written like this, it's called a ket. It's a mathematical notation and this is like really powerful. It's a very powerful notation, I would say. It was introduced by Dirac. So this kind of vectors is called ket and this is called bra. Now at the place of dot we can put any symbol which tells you what kind of Hilbert space we are talking about. In general we would write shy when we want to write something general, but you can write position, like you can say position ket, like the ket of which represent the position, some position x, the ket of spin up particle, the ket of spin down particle. Okay, so this is how we write, like this is how the notation works. You will get more familiar with it as we go along. So the idea in quantum mechanics is, if I summarize, is that the state of a vector is some abstract vector in some Hilbert space, and the observable which we talked about earlier, the observable which we use to define the state of the part of the system in classical physics, they are not used to define the state in quantum mechanics, but you can extract the observables. It's an important point, so that's why I'm writing it down. You can extract the observables from these state vectors using operators. So what really happens to the observables in quantum mechanics is that they, instead of a variable x, suppose like position x or momentum p or energy E, these are variables in classical physics. I'll write it CP for the time being. In quantum mechanics, these are not variables anymore. They become some operator. This hat symbol is to represent that they are operators. Here I'm writing H, which is the Hamiltonian operator which gives you the energy. And when you act these operators on these states, you get, this will give you, this will output, or this will spit out basically the value of variable. When I say they will spit out value of variable, I do not exactly mean that it is going to be like this. No, this is not how it is going to be. It's going to be an eigenvalue equation, and which we have to solve. So there are more technical detail, mathematical details which we will deal with later. But right now the idea is that in quantum mechanics, the state is defined with some abstract vector, and the observables, which are the quantities which one can measure, they become an operator. And when you act this operator on those abstract vectors, you can get in principle the values of the those variables which we can measure. Now how do we get that? It is not going to be like this, but as we move along you will get how it works and how you can extract the information, the value of variables or observable quantities from this abstract vector, that we will see in further lectures. Right now the most important thing to remember is that in classical mechanics we use state variables to define the state, whereas in quantum mechanics we use some abstract state vectors, and the state variables becomes the operator. Okay, and these vectors lives in some Hilbert space, and this operator acts on this Hilbert space. So in some sense you can say that the operators are a map from Hilbert space to itself. These are operators are map, whereas the state vectors are the elements of this Hilbert space. Okay, I'm using this H, but this is used for Hamiltonian. For Hilbert space we use curly H like this. It's a standard symbol. So I hope the idea is clear. I'll see you in the next video when we will discuss further about this, and we will understand how these state vectors, like what is the interpretation of these state vectors and this operator and so on. We will discuss all that in the next video, like not all of that in a single video, like one by one we will discuss all of those in a sequence which I hope will be simple to understand, and I hope it will give you a great deal of understanding of quantum mechanics. So till then, bye bye. If you like the video, please, okay, I said bye earlier. If you like the video, please like the video and subscribe to the channel for next videos, and I see you in the next video. Till then, take care. Bye bye.